तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody. In the series of lectures on basic electronics, learning by doing, we are moving on to the next lecture. You may recall in the previous lecture we discussed about Zener diode, we talked about the Zener characteristics, we tried to understand how the Zener characteristics comes in the way you saw in the last lecture, and now we will try to look at some of the applications of Zener diode. Now you know the equivalent circuit of a Zener diode can be, as I shown on the screen, it could be with a voltage source corresponding to VZ, which is the breakdown voltage, and a series resistance RZ. So this is the equivalent circuit of a Zener diode. Now we move on to the discussion on the applications of Zener diode. One of the very important applications of Zener diode is as a voltage regulator. Now what we mean by regulation? Any power supply, we already mentioned some time back in one of the previous lectures that any power supply will be equivalently represented by a voltage source and an internal resistance or a series resistance Rs. So only an ideal voltage source will have no internal resistance. The Rs will be 0 for an ideal voltage source. For all other normal voltage sources that we come across, there will always be an internal resistance, even if it is a battery, for example, or a voltage cell. It will have its own internal resistance, which is non-zero. So when I now connect the voltage source, which is an unregulated voltage source as we call it, when we connect it to a load, for example RL, as you see on the screen, you would find the voltage applied across the load resistance RL, in principle we expect it to be a constant, irrespective of what the load resistors that we connect. But because of the internal source resistance, you would find this voltage will not remain constant as we change the value of the load resistance. The load resistance here corresponds to whatever you are using the power supply for. We need the power supply to power, for example, a appliance. It could be which requires a DC voltage, for example. It could be a simple function generator, or it could be a amplifier. For all these things we require a DC source or DC power supply. So the load here, I mean, is any appliance which requires electrical energy. So when I change the load, or if the current which is being drawn by the appliance is different, it can happen all the time, then you would find the voltage which is actually applied across the load will no more be a constant unless it is a regulated power supply. To explain it little more in detail, I have shown both the circuit, the unregulated power supply on the left, and I have also shown what is its equivalent resistance. If you look at the Thevenin's equivalent resistance of this unregulated power supply, it will be equivalent to an ideal voltage source V connected in series with the internal resistance of the source, or Rs or Rin as the case may be. And this is the equivalent circuit of the unregulated voltage supply, where here Rin is a finite value and RL is the external load resistor that you apply, which can be the appliance that I was referring to. Now what is going to happen because of that? I have given a small graph to illustrate this point. For example, this is a 5 volts unregulated power supply. So you would find the y-axis is voltage, the x-axis is the current. So if I now change the load resistance, for example, I take the 5 volt supply, I connect different values of resistances across the 5 volts. For example, if I apply 100 ohms, the voltage may remain 5 volts. If I now change the 100 ohms to 50 ohms, 25 ohms, 20 ohms, 10 ohms, etc. If I keep on changing the value of the load resistance, if I keep on reducing the value of the resistance which I connect, you would find V by R corresponding to the load resistance will become greater and greater. That means the current which is flowing out of the voltage source will be increasing. If the current increases, you would find in an actual situation the 5 volts will not remain 5 volts constantly. What you expect from a power supply is the voltage should remain constant irrespective of the value of the current that I draw from the voltage source. But in reality you would find as I increase the value of the current, the voltage will keep falling. That is what is shown in this graph here. So this is a typical characteristic of an unregulated power supply, where the voltage, output voltage, is not remaining a constant, and as I increase the load current, the voltage keeps falling after some value perhaps. And so this is not a desirable characteristic of a good voltage source or voltage supply. So if you want to avoid this fall in the voltage, and if you want the voltage to remain constant irrespective of the load that you connect, then you have to do something to the unregulated power supply, and that is what is called the regulation. So you have to regulate an unregulated power supply to give a constant voltage output irrespective of the load that you connect. Now let us look at the slide. You find here an unregulated power supply with a voltage source V and internal resistance Rn connected to an external load RL. Now if you want to find out what is the voltage across the load, the VL will be equivalent to Vs, the source voltage, minus voltage across the R input, that is internal resistance. So VR in is the voltage that is developed across the R in, and Vs is the voltage source that you have, ideal voltage source, and VL will be the difference between these two, as you can see from basic KVL, Kirchhoff's voltage law. So when I have R in equal to RL, you can immediately imagine what will be the VL value. When R in is equal to RL, this voltage source will have to be divided among these two resistors, and therefore you will get only half of Vs across the load. So you can immediately see that the VL is not a constant, it depends on RL. If RL equal to 0, then you can see R is infinity. That means that if there is no load, which corresponds to the load being absent here, that means it is open circuit. Here you would find there is no current flowing, and therefore there is no voltage drop across R in, and therefore whatever you get will be the total voltage source voltage that you have. So Vs will be measured between these two terminals. So you can see as I now decrease the value of RL till I get a situation where Rin is equal to RL, you would find the voltage will drop from Vs to a value which is Vs by 2. So if I still decrease the value of RL still further, you would find the current will increase further and the voltage also will drop further. So this is going to be a problem. The voltage is not remaining constant as I change the value of RL. So, if I want a good regulation, what should be the effect? You can immediately see, if I make the value of Rin 0 or as small as possible, then you would find the voltage drop which comes about because of the existence of Rn will become less or almost 0 if it is Rin 0. So, in that situation you would find almost the entire voltage will be available across RL. So, when I say I want to prepare a voltage regulation, what I mean by that is I am attempting to make my internal resistance of the source by some means to a very small value, or if possible ideally to a value 0. So, that is what we mean by regulation, trying to reduce the value of the internal resistance, so that the output voltage will always remain constant irrespective of the current that you draw through the load. Now, let me just recall for a minute the characteristics of a Zener diode. You all would remember, I showed it in the previous lecture also. So, you have on the forward bias condition, when V and I are there, you can see it is something similar to a normal diode, but when you come to the reverse direction, V minus and I minus, then you would find it is remaining constant almost with a very small value of current up to a value which is called VZ, which is a breakdown voltage, and beyond that the Zener breaks down and you would get a very large current, but the voltage will almost remain constant. So, you can see this is the reverse characteristics. The reverse characteristics suggests to us that after the breakdown, the voltage remains constant for very large values of current, change in current. So, this is what we wanted to do with reference to regulation. So, you can immediately see how a Zener diode perhaps can be a solution for regulating an unregulated power supply. To bring things much clearer, what I have done is I have actually rotated this for some convenience. In this way, then you would find, irrespective of the increase in current, the voltage remains constant. This is nothing but the characteristics of Zener diode, but you can see here the voltage remains constant in the breakdown region for very large values of change in current. Therefore, this is what we want for an ideal voltage source or a good regulated voltage supply, and therefore, the Zener diode can be used as a regulating device in a power supply, in an unregulated power supply. Okay, now how do we do that? If I have, for example, I need to design a regulated power supply for 5 volts, then what do? You have to use a Zener diode which has got a breakdown voltage of 5 volts. If I want a voltage source of 12 volts, then I must use a Zener diode which has got a breakdown voltage of 12 volts. Right, but you should remember the unregulated power supply that you have to use to regulate should have a voltage much larger than the Zener breakdown voltage that you choose. That is, if I want a 5 volts regulated power supply, I should start with an unregulated power supply which is maybe 9 volts or 10 volts. It cannot be very close to 5 volts, which is the breakdown voltage of the Zener that I have chosen. Why is it so? It is because you should ensure that the Zener diode is operating in the breakdown region. Only in the breakdown region you find the voltage remains constant irrespective of the current flowing through the load, and therefore, you must make sure that the Zener is operated in the breakdown region. So, that is why you require much larger unregulated voltage source if I want to regulate it to 5 volts or 9 volts as the case may be. Okay. Now, let us take a simple example. If the input voltage is 9 volts and you want only 5 volts by using a 5 volts Zener diode, then you have a balance of 9 minus 5 corresponding to 4 volts, which must be dropped across another resistance in series with the Zener diode, which is called Rs. So, you would always see Zener diodes, whenever it is used in the breakdown region, you must have a series resistor Rs, which will be used to bias the Zener diode, it will be used to drop the excess voltage available over and above the breakdown voltage. Now, how do we calculate the value of RS in a given situation? For this, we should know what is the current that we would like to have, the operating current for the power supply. So, I call that IZ in this case. So, how do we get the operating current? One way to get the operating current is you should find out what all the minimum and the maximum current that can pass through the Zener without any damage to the device. We know already from the characteristics, if we go back to the characteristics, we know already that the breakdown region starts at some point which is called a knee point, and that current will be the minimum current that I must have passing through the Zener to be in the breakdown region. So, there is a IZ minimum which is dictated by, from the characteristics you can observe it. This is to ensure that any current above this will be having the Zener diode in the breakdown region. Then what about the maximum current? The maximum current will be dictated by the power rating of the Zener that you use. If you are using a Zener diode of 600 milliwatt or 500 milliwatt or 1 watt, you can buy Zener diodes with different power rating. So, if I use, for example, 500 milliwatt and then I use a 5 volt Zener and a 500 milliwatt, then you can see the IZ maximum value of the IZ will be 500 milliwatt divided by 5 volts, and you can see that it is about 100 milliamperes. So, what it means is you cannot have a current which is larger than 100 milliamperes passing through the Zener. What would happen if I exceed this current? The Zener, there will be a Joule's heating, there will be heating of the Zener, and due to the temperature effect there may be a irreparable damage caused to the Zener diode when you use it in a circuit which requires larger than 100 milliamperes current. Therefore, the maximum current is 100 milliampere, the minimum current is at IZ minimum, that is observed on the characteristics, so which is normally going to be few milliamperes, 1 or 2, let me take it as, let us say 1 milliampere. So, now what is the operating current? The best way to operate is take the golden mean, operate the Zener diode in a point which is equally away from this minimum current and the maximum current, and therefore you find the average of the IZ max and IZ minimum, that can be chosen as your operating current. In this case, you have 1 milliamperes and 100 milliamperes, and the average is approximately close to 100 milliamperes. The average is going to be 50 milliamperes, right? So, now you can choose a resistance corresponding to the 50 milliamperes. So, the RS value can be now calculated as 9 volts minus 5 volts divided by 50 milliamperes. So, that will be 4 by 50, 4 volts by 50 milliamperes. So, that is a value of resistance which will be around 80 ohms. So, about 80 ohms will be the value of RS if you want to operate the Zener diode around 50 milliamperes. Now, I have shown here RS equal to 9 by 5 divided by 100 milliamp, which is the 40 milliohms. That means you should never use a RS value which is smaller than 40 ohms if you want the Zener diode to function properly. That is what we mean here. Okay. So, again I have shown here IZ operating will be IZ minimum plus IZ max divided by 2, and average of these two values, and RS is VZ by IZ operating, from which we can calculate what is the value of RS. So, all that you have to do is take the unregulated power supply which is shown here on the left side as EI, and this is your RS, in this case shown as R, and you have your Zener diode. So, you choose the R as mentioned just now, and you put your Zener diode in the reverse bias condition, so that it is under breakdown condition, and therefore this voltage will remain constant. Now, up to what value of RL it will remain constant will have to be very carefully looked at. You can see when I put RL here, if I keep varying this, there will always be a limit. That means there will be a minimum RL value below which I cannot reduce RL, once that happens, large current will flow through that and less current will flow through IEZ, and therefore the Zener diode may be pulled out of the breakdown, and therefore this will cause the regulated voltage not to be well regulated. And therefore there is always a minimum voltage or resistance RL which you can connect, but as far as the maximum value is concerned, you can keep on increasing the value up to open circuit when the resistance becomes infinity here, and then it is just the Zener diode in the breakdown region, no other resistor connected, and therefore it will be still be VZ, the voltage across the Zener diode. So this is one simple way of making a voltage regulator using a Zener diode. We always remember that there should always be a series resistor RS connected to keep the Zener diode in the breakdown region, operating in the breakdown region. Now let me quickly show you a simple demonstration of the thing. You can see there is a breadboard and you have a power supply and you have the multimeters, everything in position. Now let me try to do two types of experiment. One in which I am going to vary the voltage input. I take a variable voltage source as an unregulated voltage source, and I want to vary this voltage and find out what happens to the output voltage. Will it remain constant? Now then the second experiment would be, I will keep this voltage constant and vary the value of the load and see what happens. So these two are called two different characteristics of a regulated voltage supply. One is called the line regulation, when I change the input voltage and see whether the output remains constant is called line regulation, and when I change the load and keep the input constant, then it becomes a load regulation. So the line regulation and the load regulation are two important characteristic of a good regulated power supply. So that is what we will just do first as an experiment. Later on we will try to understand a little more about these things. Now let me quickly switch on the power supply. First let me choose the experiment and then I will switch on the power supply. So now I have switched on the voltmeter, everything. There is 8 volts applied at the input, and this resistance is about 120 ohms in this case, and the Zener is about 4.9 volts, and I have connected a load 250 ohms, you can see. And at this end I have connected a current meter, multimeter in the current range, and I am measuring the voltage across the load using a multimeter, and that is now now let me see. So when I increase the voltage to 9 volts here, you can see the output remains constant at 4.9 and the current is 34 milliamperes. How do I get 34 milliamperes? This is 4.9 volts and this is 250 ohms. If you divide 4.9 volts by 2, okay, this current is actually the series current which is flowing through the RS, and that is actually given by V input minus VZ divided by 120 ohms. V input is 9 volts, VZ is 4.9 volts or 5 volts, and difference is about 4 volts divided by 120 ohms. That is what is obtained as the current here. Now if I increase it to 10 volts, you can see still the current is increasing but the voltage remains constant. When I go to 11 volts also, you find the output voltage remains constant at 4.9 volts. So I have varied over a range of values from 8 volts to 12 volts, and you find the output voltage remains constant, and the series current, the series current through the RS is changing depending upon the input voltage that I change, but the Zener voltage remains constant. So this can be used for regulating a unregulated power supply. Now that means now let me move on to the second part, which is basically to change the load, keeping the input voltage constant at 10 volts. I am going to change the load resistances to some fixed values of resistors here and find out what happens to the output voltage. So let me switch on the power supply and the multimeters. The same circuit that I used previously. Now I have a fixed voltage of 10 volts applied at the input, and you have a RS of 120 ohms and a Zener diode corresponding to 4.9 volts, and this is now you can see. Let me first connect a 100 ohm resistor as the load. So you have 4.9 divided by 100 volts, that is what you get as a current here, 42.5 milliamperes. Now if I, instead of 100 ohms, if I change it to 1K, now you would find it is about what happened, 42.5 milliamperes, and if I connect 10K, right, now I connect 100 ohms, yeah, the current meter is actually connected in series with the RS. It is not the load current which I am measuring. Therefore, even though I change the value of the resistors, you would find the current is not changing here, because that is this current which is being measured, which is in series with the RS. So you can in principle put a current meter in series with the load also, then you would find the load current will keep on changing depending upon the value of the resistor that I connect here. So now I move on to another resistor 10K, you would find the voltage remains constant, and if I put 100K, still it will be constant, because as I increase the current here, the load current will decrease, and therefore the total current will be divided here. Some part will move through the Zener diode and the rest will flow through the load resistance. If I increase the load resistance, more of the current will flow through the Zener diode, less current will flow through the load resistor. So you must make sure that this bifurcation of the current, input current, through these two does not exceed the maximum value of the current that is possible through the Zener diode, corresponding to the power rating of the Zener diode. Right. Now let me move on to the next part. So what we are now trying to do is, we are calling this as a shunt regulator. You are using the Zener diode as a shunt in front of the unregulated power supply, and there are, I already mentioned to you that there are two parameters which are very important for us with reference to the performance of the regulator. One is called the line regulation, the other is called load regulation. What are they? The line regulation is defined as the change in the output voltage delta V naught corresponding to a 1 volt change in the voltage Vs. So delta V naught by delta Vs is called the line regulation, and it is usually expressed in millivolts per volt. And the load regulation is defined as a change in the V naught, the output voltage, corresponding to 1 milliamp change in the load. So it is delta V naught by delta IL, the change in output voltage corresponding to a change in the load current corresponding to 1 milliampere. Now let me quickly take an example of a Zener diode which has got a fixed voltage drop of 18 volts. This Zener diode, which is shown in the figure, has got a breakdown voltage of 18 volts across it. So so long as the Zener diode is, Zener current is maintained between 200 milliamperes and 2 amperes, then what will be the value of R? Find the value of R so that the load voltage remains 18 volts, as input voltage is free to vary from 22 volts to 28 volts, and find also the maximum power dissipated by the Zener diode. This is a very simple problem. So you have a power supply whose voltage can vary from 22 volts to 28 volts, and the Zener diode has got a breakdown voltage of 18 volts, and your load is around 18 ohms, and the input voltage varies from 22 volts to 28 volts, as I already mentioned to you. Now the minimum voltage across the R will be corresponding to minimum input voltage, which is 22 minus the voltage across the Zener 18, that is equal to 4 volts, and the current through R, when the maximum current flows through RL, is the IL maximum load current plus the minimum Zener diode current. The current flowing through the Zener will be minimum, the current flowing through the load will be the maximum. That means it is 18 volts by 18 ohms corresponding to the maximum load current, plus they have already mentioned that the current IZ can go from 200 milliamps to 2 amperes. So this is about 200 milliamperes. So the total current will be 1200 milliampere, 1.2 amperes. Now therefore what will be the value of R for providing this type of a variation? R will be equal to 4 volts divided by the total current, and which is equal to around 3.3 ohms, and the maximum current through R is 28, because the voltage can go up to a maximum of 28 from 22. 28 minus 18 divided by 3.3 gives me the maximum current that can flow through the series resistor R, and that in this case is 3 amperes or 3000 milliamperes. But the IZ max is actually 3000 minus 1000 milliamperes, which is equal to 2000 milliampere, which is within the limit of IZ specified in the problem. They said the IZ can vary from 200 milliamperes to 2 amperes, and therefore 2000 milliamperes is only 2 amperes, and therefore even when the load resistance maximum is around 3 amperes, there is no harm done, because it will still be within the limits specified, and therefore this value of R is good enough. Now what is the maximum dissipated power across the Zener diode? That is given by voltage into current Vz into IZ max, and that is 18 volts is the Vz value, 2000 milliamps, 2 amps is the maximum current through the Zener, so that corresponds to 36 watts. So you have to use a 36 watt Zener diode, and then this type of a design can be achieved. Okay, now let me quickly move on to the table and show you a simple Zener regulator, and I actually use a 4.9 volt Zener, and we have used the regulated power supply as an unregulated power supply, because I can vary the input voltage and see how the output voltage remains constant. So you can see the circuit here is also shown for simple understanding. There is a voltage source here Vs, and there is this Rs. I have connected a series current meter, milliammeter, and this is your Zener, which has got a breakdown voltage of 4.9 volts. Then I also want to measure the load current, therefore I have introduced one more current meter in series with the load RL, and what I measure across the RL is the output voltage V0. So now you can see I have a series resistor which is around, I think, 100 ohms here, and I have a Zener diode. I hope you can see the Zener diode here. This is the Zener diode, which has got 4.9 volts breakdown voltage, and this is the load. And now I have connected the input from a regulated power supply, the plus and minus terminals, and I have connected the one current meter, which is actually this is the current meter corresponding to the series resistor Rs, and now let me switch on. This is the current meter. So I have switched on the two multimeters. I have kept this in current mode, and I have kept it in DC current here. I have selected DC current. Similarly, I have put it in voltage mode and kept it in DC volts mode. Now everything is ready. You can see this current meter is this, and this is the Zener diode, and this current meter is here, and this voltmeter is here. So you try to observe. Now I am going to switch on the power supply. I have kept around some 8 volts. You can see the current is around 8 volts. Now let me see what is the you can see the voltage is around 4.8. the current here is about, the load current is around 15 milliamperes. Now if I decrease it little bit, you can see the current, the series current also decreases, right, and if I come below 4.6, this voltage is also decreasing, the Zener the voltage across the load. If I bring it above some 6 or 7 volts, you would find, for example, it is about 7 volts. Now you find it is around 4.7. If I go still further, for example 8.3, it is still around 4.8 volts. If I go to some 10 volts, you would find still it is around 4.9 volts. So irrespective, if I change the input voltage, the output voltage is not changing, it is remaining constant, very close to about 4.9, but the current is around 5.54 across the load current, and this current has actually increased enormously. Maybe I should have shifted the two multimeters, it does not matter. So you can see if I change the input voltage, the current is changing, but this voltage across the Zener remains a constant 4.9. This current will also be remaining constant, because that is dictated by only the load resistor that I have connected. So 5.9 divided by this is around 330 ohms I think, and therefore it is around 15 milliamperes. Now if I take out the resistance, I will keep it constant at this point. I remove the resistor, load resistor. Now you find the current becomes 0 here. The current is 0 because I have removed the load resistor. In place of that, let me connect a larger value of resistor, for example 1 kilo ohm resistor. When I connect a 1 kilo ohm resistor, you would find correspondingly the current has decreased to about 5 milliamperes, but the voltage remains constant at 4.98. So but the input current is nearly more than 25 milliamperes, so the rest of the 20 milliamperes will be flowing through the Zener diode, right. Only 5 milliamperes flows through the load, the rest of the current is flowing through the Zener diode. So similarly I can still increase the load resistance by removing the 1k resistor. Let me connect a 10k resistor. Now you can see the current has become 0.5 milliamperes, 500 microamperes, and the voltage is 5.06, very close to 4.9. So you find this voltage is still remaining constant, but this current has decreased, load current, and this input the series current is high as ever. No, all the time it was high. So you can see a Zener diode can be used to regulate a unregulated power supply, and we can now calculate by changing here by a very known value, find out what is the change in the output voltage. That will tell us about load regulation, line regulation, and similarly I can vary the current here by changing the resistance and find out by how much the voltage is changing. For a 1 milliampere change in the current, if I calculate, that will correspond to the load regulation corresponding to the Zener regulator. Now you see that we do have a good regulated power supply when we use a Zener regulator, Zener diode as a regulating device. But unfortunately you can see, if I want larger current, say 1 amperes or 10 amperes as the case may be, you find I must use a Zener diode which has got a large power rating. So as I want larger and larger current for my load, I have to go in for a Zener diode which is having much higher power rating, and the Zener diodes which higher power ratings are, as you all can expect, will be more expensive. They are very expensive compared to the Zener diode with some 500 millivolts or 300 millivolts as the case may be. So is there a way to improve the current output from a Zener regulator? The answer is yes, we can do that by using an additional transistor. I have not discussed yet about transistors, but still it is very easy to understand here as a simple application, and the details of the device will be discussed in a later lecture. Now I will just mention to you as an extension of the regulation principle how a transistor can be used to boost the current at the load, having even a Zener diode which has got a lower power rating. That means even though I use a normal Zener diode which has got about 500 milliwatts power rating, I can still have much larger current than what I would normally calculate as my IZ max, because now I use a transistor. Basically you can understand for the present the transistor as a simple current amplifying device. So if I have a base current IB here, I will get a collector or a emitter current which will be several times larger than the base current. That is the basic feature of a transistor. So this current amplification is called beta or HFE, which we will discuss a little later. So this multiplication factor which is coming between the base current and the emitter or the collector current of a transistor is exploited in this case to design a regulated power supply which will give me a much higher current rating than what I would otherwise get from a normal Zener diode. So the configuration is as shown in the figure. You can see I do have the RS still, the series resistor, and you have the Zener diode, and the junction of these two is connected to the base of the transistor, and the collector is connected to the unregulated power supply, and the emitter is connected to the load. This configuration, even though it looks slightly complicated, you can see I have drawn it in a different way here, side by side. This is the old circuit and this is the new circuit which I have drawn for simplicity, because some of you may be able to identify this as a very simple configuration of an emitter follower. Okay, we will discuss about this little later. The characteristic of the emitter follower is that it will make the output impedance very, very small. Regulation means reducing the internal source resistance of an unregulated power supply to a very minimum value, and a emitter follower has got low output impedance. Therefore an emitter follower output can become a part of a regulated voltage supply. That is the principle behind this here. So even if there is a very small current IB here, I will have nearly 100 times or 200 times, depending upon the current gain of the transistor, the value of a load current can be about 100 to 200 times larger value, and therefore this simple transistor which is called the pass transistor here can be used to boost the current capability of a Zener based regulator circuit. So that is what I want to mention to you here. Now in a more involved circuit, complicated circuit, you can in principle use an amplifier which will amplify the input signal to a larger value, and in this amplifier it is actually a difference amplifier here. That means it amplifies the difference in voltage at the input, and the difference in voltage, as you can see, is here between the voltage across the Zener diode is connected to one part of the amplifier, the other part is connected to a point which is provided by the potential divider. R1 and R2 at the output are provided as a potential divider, and this point is connected to the other end of the amplifier. Therefore this amplifier, which is a difference amplifier, will look at the difference in voltage between VZ and a point which is proportional to V output. This voltage will be V output multiplied by R2 divided by R1 plus R2, that is a potential divider that we already discussed in the earlier lecture. Therefore this voltage is going to be proportional to the V output. So if the V output changes, this voltage can change, and therefore if this changes, this is not going to change because it is a Zener diode, and in the breakdown region this voltage will remain constant. Only this voltage will change. So if it changes, there will be a corresponding amplified voltage here, which will make this transistor which is used here in this application as a variable resistor. So this variable resistor will vary in the value of resistance and thereby keep the voltage across the load constant. That means it is regulating the output voltage by using the pass transistor T, the transistor that you have here, by using an error amplifier here and a Zener regulator. This is a slightly more involved circuit, but this is very useful for regulating unregulated power supply. Nowadays we have standard regulated power supplies can be obtained very quickly by using what are known as three terminal IC regulators. Okay. Before I go into that, I want to just mention to you that you would always have a situation where the value of the load will be reduced to such a low value that therefore you will be drawing a very large current, so which may sometimes damage. For example, if by inadvertently if I connect a wire between the output terminals, it corresponds to short circuiting the power supply. When you do the short circuiting of the power supply, that means you are almost connecting zero resistance across the terminal. This will correspond to a very large current flowing through the regulator. This might spoil the devices inside. Therefore, if you want to avoid that, that means if you want to protect the power supply or the regulator against short circuit, any inadvertent short circuit, then you have to design a current limiting circuit. So the idea behind the current limiting circuit is to use a resistor here R10 between the base and emitter of a special transistor, additional transistor. This is different from the earlier transistor I used, and this transistor has got a resistor R10 between the base and emitter, and it comes in series with the load current. So when I increase the load current, there will be a voltage drop across that. As long as this voltage drop is less than the voltage required to forward bias this transistor, you would find nothing will happen, the load current will flow. But when I draw a large load current which makes the voltage drop across R10 nearly 0.7 or little more than that, you would find this will make the base of this transistor larger in voltage than the emitter by this voltage across R10, and if it is 0.7 for example in the case of silicon, this Q3 will be switched on. When it is switched on, you would find the current will start flowing through this, it will avoid this Q1 transistor, and therefore the output will be almost reduced to 0. You will be drawing a maximum load current through the transistor, but the output voltage will become 0. So when I short circuit the current beyond the load current that I set, you would find I can make the device to close. Therefore the output will become almost 0, and therefore no damage will be done, because there is the current will be bypassed through another path, and therefore no damage will be done to the device that is being used in the regulator. So now this feature, how do I choose the R10? I can easily choose R10 by knowing what is the maximum current I want to limit. For example, if I want 1 ampere current, I will have to have 0.7 volts here to make this transistor on for forward biasing the transistor in the case of a silicon transistor. Therefore 0.7 voltage divided by I 1 ampere is around 0.7 ohms. If I connect 0.7 ohms in place of R10, I will have a maximum current of 1 ampere, and if I try to exceed the current beyond 1 ampere, the output will be almost close to 0. So that way we can calculate the short circuit, the current which I want to limit, the value of the current. Okay, I have shown the characteristics here corresponding to that. This is voltage output versus load current, and when the load current increases initially, because it is a regulated supply, you find the voltage remains constant for a large value, and then when I increase the IL max, which is the maximum rated current, you would find this immediately the output voltage drops to 0, and the short circuit current will be a slightly larger value than the IL max that we have seen. And so this is one type of current limiting that is being employed. There are several other types of current limiting circuits that can be used, but a good voltage regulator should be having a constant voltage, and it's also in principle be protected against any short circuit. And therefore I just want to highlight these two aspects of a very good regulated voltage supply. Now I have also shown to you here how we can use a 3-terminal regulator, integrated circuit regulator, which are now very popular, and you can make quickly in the lab a regulated power supply. We have already seen how you can make a unregulated power supply by of any value. For example, you want you use a bridge rectifier here, you use a transformer, step down transformer, which will give output voltage which is around 20 volts or 12 volts as the case may be. Then I can use a bridge rectifier in the following mode, which we have already discussed, and output I have put a capacitor here which is about 1000 microfarad or something to filter out all the ripple voltages, and then I can just connect a 3-terminal regulator which has got 3 terminals as it is mentioned. You have an input, you have a ground and you have an output. What is the circuit that we have here? If you ask, it actually contains the different circuits that I just now mentioned. You have a internal Zener regulator, regulated power supply with a Zener regulator and a pass transistor and a current limiting device, all built in integrated circuit form. And therefore, if I give the input here and if I take the output here, the output will be a constant value. What will be the value of the constant is given by the last 2 digits of this IC number. 7812 for example means it is a 12 volts positive regulator. So the output voltage will be positive and it is around 12 volts. So it is very easy for us to build a regulated voltage source by using a very simple transformer, bridge rectifier and a filter capacitor and a 3-terminal IC regulator. One can also make a negative power supply. So before I go that, maybe I will just show you the actual circuit of a positive voltage regulator. So you can see this is the positive voltage regulator in TO221 package. That is a outline, transistor outline package that you have here. It is, you have just got this an IC regulator, as I mentioned to you. It is not a transistor IC. It has got 3 leads. One is the input, the other is the ground, and the third one is the output. So I connect it to the breadboard here, and I have a diode rectifier, bridge rectifier here, and I have a transformer here. Now I switch on the power supply and I switch on the voltage and the current meters. Now you can see the output voltage is 12 volts, and because I have not connected any load, the current is 0. If I now connect a 100 ohm resistor, you will find it is around 120 milliamperes. Because this is 100 ohms, 12 volts is the output, so I get 120 milliamperes. If I change the resistor, I can change the different load resistors, and you can see the correspondingly the load current also changes. So this actually measures the load current, this measures the output voltage across the load, and you would find the load remains constant 12 volts for different values of resistors that I have. And as I already mentioned to you, this IC regulator is also short circuit protected. We can also design a power supply, regulated power supply with negative output voltage. You require both type of power supplies. So here for example again you have transformer and a bridge rectifier, but in this case you use a IC regulator which is a negative regulator, and it is 7912. 7812 is a 12 volts regulator, 7912 is a negative voltage regulator, and you should remember this negative end is connected to the ground, and the negative end is connected to the IC and the positive end is connected to the ground. Therefore this becomes a negative regulator, and rest of the circuit details are similar to the one which we already seen, and therefore this provides a negative voltage regulator. If I combine these two, I can have what is known as a dual power supply. You can have both positive and negative outputs with reference to a common ground or 0, and therefore this will be very useful when we go into operational amplifiers, which some of them they require dual power supplies. That means you require both positive and negative output with reference to 0. Now let me quickly show you the circuit of a negative Zener negative regulator, IC regulator. Again you can see there is a bridge rectifier, this is a transformer output connected to the bridge rectifier, and a filter 1000 microfarad capacitor is connected here, and you have this regulator. It is similar to the positive regulator except that it is 7912 corresponding to negative voltage, and the rest of the voltmeters are all there. And if I switch on the power supply and the multimeter, you would find the output is minus 12 volts. And if I now apply different currents, you can get correspondingly different load currents corresponding to the different loads. So in principle one can quickly build a positive voltage regulator or a negative voltage regulator, as the case may be, corresponding to the one that he wants to use in the lab by using this type of a simple arrangement. So that is what I wanted to give you. Now let me quickly show how we can also go for a dual power supply, a split power supply regulator. Here again you have the same transformer, but again you have a center tap transformer, and the center tap is maintained as the common terminal 0, and you have both 7812 and 7912 connected as shown in the picture. The positive is connected to 78, the negative end is connected to 7912, and the capacitors will have to be carefully connected in the circuit in proper polarity, and then you will get 3 outputs, 0, plus 12 volts and minus 12 volts. All can be obtained by a very simple configuration as shown in the picture. I would perhaps show you the actual working of this positive regulator or any one of the regulators in the next lecture before I go on to the next topic, which is about transistors and their characteristics. Thank you.